What up, ladies and gents? We are going to really be making a video right now of all of the equations that we are going to be using in Unit 2. You noticed we've just been looking at graphs. We've been looking at graphs and motion maps. What we're going to do now is actually start to wrap this up in a more mathematical sense with equations. Before we do that, though, one of the things that I'd like to do is make our lives a little bit simpler, because if you've noticed, we've been writing out these really long words like position, displacement, and when we start using equations, we actually have short names that are going to be replacing those variables. So let me zoom in real quick and give you a nice look at this table. I'll say copy down this table. I'm going to talk briefly about a couple of key ideas with each one of these. So, position. Position can be labeled as a short name, either X or Y. You might say Y, haha, no pun intended. If we go on over here, you'll notice X in this case is referring to an object that might be moving left or right, that is moving in the X directional position. Y is going to be referring to something that might be moving up or down. Those are just in replace of our standard positions, kind of like moving on our X positional axes or our Y positional axes. And you'll see our common unit for position will be meters, but it doesn't necessarily have to be meters. It can be kilometers, it could be miles. Stupid thing, don't show me that again. Alright, so displacement is going to be very similar, because remember, displacement is the change in position. So the way that we do that is we use this little delta. You've seen that hopefully in math. The delta is a little triangle, and all it's telling you is final minus initial. So anytime you see a delta x, you can always replace it with this. Feel free to do that. XF is of course referring to the position final, and XI refers to the initial position. Speed, there's actually no short name for that, so I'm going to ask you to just write it out. Some books have used S. I don't like S just because it refers to our seconds, which can be kind of confusing. So I'm going to say let's just keep it and just write it out as speed. Velocity V. Time, T refers to a specific time, and then delta T refers to over a time interval. So I want you to kind of take a closer look at that. We will start using those differently as time goes on. Ha ha ha, no pun intended there. Oh, I'm on a roll. And initial position there. I will on occasion throw out this x0, and I will call it x naught. This is how the physics community uses it. It really means x at time equal to 0. That's what the 0 is referring to. So sometimes you might see x2 as referring x at time 2. You can start to look at that. I like just x0 as initial position and x as being a position at some time t. So, huge thing, and this will affect you on tests. X equals 5. If you see x, or if I see x equals 5 meters, what I am seeing is I am seeing that you are saying position equals 5 meters. If you have been that person who replaces everything with x because you're like, I love math, and oh, I just love x and y, they are my favorite two variables to use, you will start to get points taken off, because I see x and y as positions. Please start using the variables that we have. If you're solving for v, you should be writing v equals. So make sure that you are doing that. So our new equations, again, this is why I try to take you away from y equals mx plus b. We will have equations like x equals 5 meters per second t plus 3 meters, and that refers to position equals 5 meters per second times time plus 3 meters. So a very simpler way, shorthand way in order to do that. Part 2 of our amazing video here. From our lab, what we actually need to start doing is coming up with equations. So what we are going to do is we're going to look at our lab. I've marked in different things that we have here. You'll start to notice that we know the slope is velocity, which I've written in as v. We know our initial position, x naught or xi, however you'd like to write it, is right there. And interesting enough, t is up here. And so what I can do is I can actually call this position what we will call x, because remember x refers to x at time t. So when we move on over here, we can actually create a general mathematical model which tells us, okay, y equals mx plus b, or in our case, x equals vt plus xi, or if you want to be fancy, you can write xo. This is the way that I will use it in our equations, but xi, if you want to replace it there, that's no problem. Remember, xo refers to the initial, which then this x naught refers to the initial position, and x on over here refers to the final position at t. So it's kind of the idea, if I plug in a time in between the 2 points or some t, 5 seconds, this is referring to the final position at that 5 seconds. So this is one of our mathematical models that we will use. You will get this equation on the test. However, you do need to realize this equation only works as what we did it for our lab. It only works for constant velocity. I'm going to put like 10 stars next to that. Okay, I lied. I'm going to put 5. Getting the idea that this equation only works for constant velocities. If you have a car that changes velocities somewhere in between, you are going to have to break it up into the 2 chunks. So constant velocity is only for this piece. So that's one of our equations. The other thing that I want to take a look at, and here's an example, is average velocities. So I have this crazy graph that I've drawn in here, and I think this really helps us out with average velocities. So I draw on this graph, and the first thing that I want to do is start taking a look at slopes. I'm going to use color just for kicks. I notice that the slope, or the velocity for this first second, is going to be 100 over 1, or a solid 100 meters per second. We are cruising. And then from 1 second to 51 seconds, you'll notice that again, I've changed my position by 100, but I've done that over 50 seconds. And you're going to notice that my velocity is going to be 2 meters per second. So we have 2 velocities here. We have a velocity of 100 meters per second and a velocity of 2 meters per second. The question is, what is the average velocity? Or better yet, what is the average speed? We're going to start out with average speed because I think it'll be really easy to think about. Average speed... Couple of schools of thought. Some people would go 100 meters per second plus 2 meters per second and divide that by 2, and we have 102 divided by 2, which is equal to 51 meters per second. The problem is, did we really go 51 meters per second for the entire 51 seconds? And the answer to this question is no, because you'll notice we're weighing both of these things equally. We're saying we went 100 meters per second for the same amount of time as what we did the 2 meters per second. And you realize a 51 meters per second over 51 seconds, that's actually quite a long distance. And you'll notice that for the majority of it, we really went 2 meters per second. So this is a horrible calculation. We don't actually want to use that. The way that we do these are these average speed calculations. And again, you will get this for the test. It is going to be total distance over the total time, delta t, for that instant. So in this case, you'll notice that our total distance traveled in this 51 seconds is going to be, I'll let you think about it for a second, total distance for the 51 seconds, you'll notice that we traveled 200 meters. We went there and back, which is a total of 200, over 51 seconds. So you'll notice if we do 200 divided by 51, we get an answer of 3.92 meters per second, which in comparison to the 51 seconds, it's like, oh wow, or 51 meters per second, you'll realize, oh wow, this is actually a better representation of our motion because we traveled about 2 meters per second for the majority of our time, but that 100 meters per second at the first second really does change the value, and it does make it a little bit larger. So our average speed calculation, you'll notice, is going to be this. That is the equation that we need to know. This will be given to you on the test. Average velocity. Remember, velocities deal with direction. So average velocity in this case is actually going to be the total displacement over the total time. And if we set this up, you'll notice, interesting enough, our average velocity for this whole thing is going to be our total displacement which is going to be 0 meters, because we started and ended in the same position, divided by our total time, which is 51 seconds, and that doesn't even matter. You're going to notice our average velocity is going to be 0 meters per second. So, looking at this, we have two new equations that are going to creep out of here, average speed and average velocity. Average velocity, again, just one last note on this, is it is taking the slope of the two endpoints. So my endpoint was here and my endpoint was here. So average velocity for 51 seconds is actually just connecting those, and you'll notice that that is a big fat straight line. If I wanted to know the average velocity between the first couple of seconds, let's say up here, what you do is you just connect those two and you'd say that is the average velocity between those, which starts to make sense because it takes a look at total displacement over total time. Again, if you have any questions, please ask tomorrow during class. We're gonna finish up the rest of the worksheet and take our quiz, and then we might start this next worksheet. Otherwise, please take a look at the example video. The example video is going to start wrapping some of this stuff up with different problems that we'll be taking a look at. Guys, have a good night, and I'll see you tomorrow.